Welcome to This Explainer. Today we're uncovering the hidden monsters of machine learning. When we think of AI, we usually picture these sleek algorithms and massive supercomputers. But the reality? Well, it's a lot messier. The truth is, the whole magic of AI absolutely boils down to the grueling, critical reality of data preparation. I want to kick things off with this amazing quote from a software engineer at Google Translate. They said that most of the times when they try to manually debug interesting-looking errors, they could be traced back to issues with the training data. I love this, right? Because it completely validates what we're talking about today. Even at a massive tech giant like Google, huge algorithmic failures almost always trace back to one thing: bad training data. And honestly, that brings us to the absolute foundational rule of data science. Remember this phrase: garbage in, garbage out. You could have literally the most brilliant, complex mathematical models on the planet, but they absolutely cannot fix trash data. It's that simple. If you feed an algorithm garbage, it's going to learn garbage, and, well, it's going to output garbage. So here's our roadmap for This Explainer. We'll start with the garbage in, garbage out pipeline, check out the scale of data, and then tackle a mathematical headache called the curse of dimensionality. After that, we'll ask, can we trust humans? And finally, we'll look at solving human unreliability with the kappa measure. All right, section 1, garbage in, garbage out. Let's dive right into the data pipeline and see what actually goes down before data ever reaches an algorithm. Let's walk through this preparation pipeline chronologically. First off, we collect the raw data. Then we identify features, select our sampling strategy, and create the data splits for training and testing. After that comes the really gritty work of cleaning and exploring the data. And finally, feature engineering. This whole transformation process right here, this is where the absolute heavy lifting of data science actually happens. Moving on to section 2, the scale of data. We're dealing with billions of samples these days. And honestly, that sheer volume changes the whole game. Just think about the stark contrast in scale for a second. Take the classic iris flower dataset, for example. It's a famous academic dataset with just 150 total samples. Now, compare that to Google's Gmail Smart Reply, which uses 238 million training samples. Or the Google Books Ngram with 468 billion. And Google Translate, we're talking billions or even trillions of samples. Making the jump from 150 flowers to trillions of data points introduces a whole new set of technical nightmares. Which brings us to our first hidden monster. Section 3, the curse of dimensionality. Let's explore this mathematical terror. Here's how we actually define this monster. As the dimension d of a feature vector grows, which in deep learning basically means the number of trainable parameters, the complexity increases exponentially. Algorithms with a big O of n times d squared complexity become basically impossible to run accurately as you keep adding features. If your sample size n is too small to estimate those parameters accurately, your model becomes way too complicated for the data you have. And that leads directly to severe overfitting. Let's picture how this builds up. Imagine we want to use a nearest neighbor approach, and we're starting with just one feature, so a 1D line. To maintain a nice, good, dense representation of our data, let's say we need 9 samples per unit length. Pretty simple so far, right? But what if that single feature just doesn't separate our classes well enough? So we decide, hey, let's use 2 features. Well, this perfectly illustrates the trap. Just adding one single feature to make our data two-dimensional suddenly demands 9 squared, or 81, samples, just to maintain that exact same density we had before. And it gets crazier. By the time we hit 3D, adding just a third feature, we suddenly need 9 cubed. That's 729 samples. In general, for d dimensions, you need n to the power of d samples. This just proves how data becomes terrifyingly sparse, and how models inevitably overfit as dimensions grow exponentially. So, the absolutely crucial takeaway here is this golden rule of thumb. You need at least an order of magnitude more examples than trainable parameters in your model. This is exactly why simple models running on huge datasets can actually beat out really fancy complex models running on tiny datasets. Okay, so we've looked at the math of dimensionality, but what about the humans actually creating all these data points? Let's get into section 4, can we trust humans? Let's weigh the pros and cons of human-labeled data. On the plus side, humans are still way better at making complex, nuanced judgments than machines are. And human annotation gives us a really realistic idea of just how difficult a task truly is. But the cons? They're massive. We're expensive, especially when you need an actual expert. We're incredibly time-consuming, and honestly, worst of all, we are famously unreliable. Let me spell out exactly how human unreliability can completely ruin a dataset. Sometimes it's as simple as skipping a value during manual form entry or accidentally entering duplicate data. Sometimes we get noisy feature values just because a sensor malfunctioned or the environmental conditions were off. But the real headache? Subjective human annotation. Think about a weird, ambiguous phrase like all except him is good. Is that positive? Is it negative? Ask 5 different humans and you'll probably get 5 completely different labels. So I want you to consider this paradox for a second. If human annotation is inherently flawed and completely subjective, how on earth can we mathematically prove that our manually labeled data is actually good enough to train a reliable algorithm? Well, that brings us to Section 5, the kappa measure. This is our mathematical silver bullet for dealing with human unreliability. The kappa measure is this incredible statistical metric built specifically for categorical judgments. The formula is kappa equals the proportion of time judges agree minus what agreement would be by pure chance, all divided by 1 minus that chance agreement. I want to highlight its absolute superpower here. It mathematically corrects for chance. It completely strips away those times your human judges just got lucky and happened to guess the exact same thing. Let's walk through a real-world example to see this in action. Say we have 2 judges categorizing 400 total documents. They aligned beautifully on 300 relevant documents and 70 non-relevant ones, but they totally clashed on 30 of them. By running these numbers through our formula, we track where they align, calculate the probability of random chance, and spit out a final kappa score. In this specific scenario, doing the math gives us a kappa score of 0.776. Okay, so what does the 0.776 actually mean? Let me give you the scoring threshold so you have a totally practical benchmark to take back to your own data projects. A kappa greater than 0.8, that means good agreement. Between 0.67 and 0.8, which you'll notice is right where our example landed, means you can really only draw tentative conclusions. A kappa of exactly 1 means total flawless agreement, while a kappa of 0 means your annotators agreed entirely by pure blind chance. To wrap up this explainer, I want to leave you with a pretty provocative thought. If your machine learning model is quite literally only as reliable as the messy, high-dimensional, highly subjective human-labeled data it trains on, what hidden flaws are lurking in your datasets right now? It is an absolutely vital question for anyone building or using AI today. Thank you so much for learning with me, and I highly encourage you to go out and deeply audit your own data.